Imagine a C++ code base that, just compiles perfectly. Like all 154 tests pass in release mode.
Right. It's highly optimized, ready to ship, just seemingly flawless.
Exactly. But then the second you switch your build system to MSVC debug mode, specifically to look under the hood and trace the execution, the entire system violently implodes.
Which is wild. You go from a completely clean bill of health
Yeah.
to this scenario where, like, 9 tests pass, 1 fails with a brutal memory fault, and 144 tests are just completely skipped.
Yeah, skipped because the test runner itself just gives up and dies.
It completely violates the basic expectation of software engineering, right?
Yeah.
The idea that the diagnostic tools we use to observe a system shouldn't, fundamentally alter the reality of the system itself.
Exactly. But today, we're going to explore exactly how that happens. Welcome to this deep dive. Today, we're looking at this incredibly detailed slide deck and presentation notes from 2026.
Yeah, put together by developer Lux036.
Right. And it's titled The Windows Debug Crash, Conda FMTSPD log std.string ABI mismatch.
Which sounds like a mouthful, but it is a phenomenal teardown of modern software development complexity. Like, even if you aren't writing C++ every day, the core theme here is just vital.
Totally.
It's a profound lesson in systems architecture. It really illustrates the massive blind spots that emerge when our overlapping layers of abstraction, so, package managers, build tools, compilers, when they just silently disagree with each other behind the scenes.
Okay, let's unpack this. Our mission today is to decode this specific catastrophic failure and trace it down to its absolute root cause.
Right, going all the way down.
We're going to look at how invisible configurations hiding inside our development environments can just completely bypass all our standard safety checks.
And we start with the anomaly itself.
Yeah.
Because the specifics of the failure are striking. When the developer switches to CMake debug using Microsoft Visual C++ C or MSVC, the failures aren't minor logical errors.
No, not at all.
We're looking at 7 distinct crashing test cases.
Right. Files with names like test lktrevis.cpp failing with a sigzig v, which is, a direct segmentation fault indicating an invalid memory access.
Just a hard crash.
Yeah. Then you have files like test.globalrouter.cpp failing with a terminate handler, which basically means the C++ runtime encountered this unrecoverable exception and deliberately halted the process.
But the critical piece of evidence here, like the detail that instantly elevates this from a standard bug to a systemic failure, is that all 7 of these crashes happened with exactly 0 assertions executed.
Wow. Which is incredibly telling, right?
Exactly.
Because if 0 assertions are executing, that means the crashes happen well before the testing framework even takes control of the execution thread.
Yes, the runtime is basically blowing up during static initialization or maybe dependency injection deep inside the device modeling engine and router code.
So the actual tests never even get to run.
Precisely. If the source code itself hasn't changed, but the program is crashing before main or the test runner is even properly initialized, you aren't looking at a logic error. You are looking at a fundamental environment breakdown.
It's basically like having a car that drives perfectly on the highway, but the moment you plug in the mechanic's diagnostic tool, the engine just spontaneously explodes.
That is a perfect analogy.
But I have to push back a little here. If the code is identical, how can merely looking at it in debug mode actually break it?
Well, since the code base hasn't changed, the environment is literally the only remaining variable. And the developer verifies this, right? They use a git stash to run a baseline comparison.
So testing an older, unmodified state of the code base.
Exactly. And it still crashes in debug mode. This proves it's not a recent regression. It is a latent vulnerability that has just been sitting there all along.
Which immediately brings us to the most unsettling part of this entire scenario, the continuous integration pipeline.
Yes. The CI system.
Because we rely on CI to ensure our code works across all environments before it gets merged. And the developer looks at the CI dashboard, the rerun list, and it is completely green.
All pass.
The automated tests are passing. So why is the CI system giving a huge thumbs up to a code base that instantly crashes on the developer's local machine?
What's fascinating here is that the CI system wasn't necessarily failing. It was just testing an alternate reality.
An alternate reality.
Yeah, you have to look at the exact matrix of the CI environment. First off, the CI was only running a release build. It wasn't even validating the debug configuration at all.
Oh, wow.
But more importantly, the CI environment on Windows wasn't using Conda.
Conda being the package manager they were using locally to pull in precompiled third-party libraries.
Right. Because setting up Conda environments in temporary Windows CI runners can add a lot of overhead. So the build system was configured to fall back to a tool called CPM.
Okay, and what does CPM do differently?
Well, CPM doesn't download precompiled binaries. Instead, it uses CMake's fetch content to pull the raw source code of all dependencies, and then it builds them locally from scratch alongside the main project.
That is a massive discrepancy.
Huge.
The CI is pulling source code and compiling everything with this unified set of compiler flags. But the developer's local machine is downloading precompiled binary packages via Conda.
Exactly. It perfectly highlights the paradox of CI systems. Like, they're designed to give us confidence that our code will work in production, but when the CI environment drifts from the local development environment,
It generates false confidence.
it creates a massive blind spot. The tool designed to catch the bug was structurally incapable of seeing it. So, the developer is completely isolated here.
Right, they can't rely on Git history. Their automated pipeline is totally blind to the issue. They literally need runtime forensics.
But the notes mention the developer didn't have cdb.exe, which is the standard Windows debugger, actually installed on their system.
Of course not, right. So they have to pivot. They turn to MSVC address sanitizer, or ASAN, which, is a really powerful memory error detector that injects instrumentation directly into your compiled code to track every single memory allocation and access at runtime.
ASAN is an incredible tool for sure, but enabling it in an MSVC environment with strict compilation flags is just notoriously difficult.
Yeah.
The developer had to navigate some severe configuration hurdles just to get the code to compile.
Let's talk about those hurdles, because they are just a great example of toolchain friction. The project was using the /WX flag, which treats all compiler warnings as fatal errors.
Right, a very strict environment.
But when you inject ASAN into MSVC, it can interfere with the default exception handling models, generating just a flood of warnings.
Exactly. To bypass this, the developer had to specifically append the /EHSC flag that explicitly tells the MSVC compiler to use the standard C++ exception handling model.
So that suppresses the generated warnings so the WX flag doesn't halt the build.
Right. But it doesn't stop there. On top of that, ASAN on Windows relies on dynamic runtime libraries, meaning the developer had to manually locate clangret.asandynamic-8664.dll and inject it directly into their system path environment variable.
Just so the executable could even find it at startup.
Yes, it's intense environment surgery just to get a diagnostic tool to run.
But the effort pays off, right? The moment ASAN is hooked up, it catches the memory violation in real time. It flags a mempy, a memory copy operation, attempting to read exactly 10 bytes of data from memory address 0x000000000000.
It's trying to read from a null pointer.
And it isolates exactly where this is happening. The program is trying to copy data to create a name string for a tree node object. The source of that data is a standard C++ std.string object.
But that string is fundamentally corrupt.
Right.
And this is where the developer employs a really brilliant debugging tactic. They trace the creation of that corrupt string to a specific line of code utilizing the FMT library, which, is an industry standard, widely used formatting library in C++ form.
Yeah, super common.
The line of code is literally just fmt.format, open parenthesis, quote, end curly braces, quote, comma 0, close parenthesis.
Which should just return a simple string, right? Just N0, a two-character string.
Yes, but address sanitizer is actively blowing up the process with a hard termination when the memory violation occurs. And when a process terminates that violently, the standard output buffers like std.count, they just don't get a chance to flush their contents to the console.
Oh, so the text is trapped in memory and destroyed.
Exactly.
So you can't just throw a simple print statement in there to see what the string looks like, because the crash kills the print statement before it ever hits your screen.
Right. So to bypass the buffer flushing issue, the developer routes the output directly to a file stream using a temporary auth stream.
That's clever.
Writing directly to a file bypasses the console buffer entirely, ensuring the physical log is written to the disk before the runtime collapses.
And the data captured in that file is just bizarre. The FMT operation, which again should have produced a two-character string, was returning a std.string object that claimed its internal size was 15.
15.
Yeah, and its actual data pointer was completely empty and null PTR. The string wasn't being corrupted later in the execution. It was literally born corrupted at the exact moment of formatting.
So to isolate the variable, they removed fmt.format from the equation entirely and just constructed the string manually using standard C++ library calls.
And what happened?
The test passed perfectly. The FMT library was the direct source of the corruption.
But the FMT library is rock solid. It's used in countless production systems globally. The logic of FMT itself isn't broken.
Exactly.
So the developer runs a dependency inspection tool, dump-in/dependence, against the debug executable to see exactly how it is linking to the FMT library. And they find the root of the entire system failure.
The smoking gun.
The debug executable isn't linking to a debug build of FMT. It is dynamically linking to a pre-compiled, release-built version of fmt.dll that was provided by the Conda package manager.
And that brings us to the core mechanism of this entire failure, the application binary interface, or ABI, specifically an ABI mismatch at the compiler level.
Let's dig into the ABI mismatch here, because MSVC is notoriously famous for fundamentally altering memory layouts based on compiler macros. And this whole crash hinges on a hidden MSVC macro called iterator debug level.
This is one of the most critical nuances of developing on Windows with MSVC. Think of an ABI as the strict physical blueprint of an object in the computer's memory.
Okay.
When you define a std.string, the ABI dictates exactly how many bytes the size field occupies, how many bytes the capacity field takes up, and the precise memory offset where the data pointer actually sits.
It's the structural physics of the object.
Yes, exactly. Now, in MSVC release mode, the iterator debug level macro is defaulted to 0. So the compiler generates this highly optimized lean memory layout for the string.
Yeah.
But the moment you switch to MSVC debug mode, that macro is set to 2.
Because debug mode injects like heavy diagnostic tracking.
Yep.
Exactly. When iterative debug level is set to 2, MSVC physically alters the structure of standard template library objects. It injects extra fields and proxy objects directly into the std.string struct to help developers track down iterator invalidation and memory leaks at runtime.
Here's where it gets really interesting. Because the physical structure of the object changes, the byte offsets for everything shift.
Right.
Like the size field might be at offset 16 in release mode, but offset 24 in debug mode. It's like writing down a set of coordinates on a map that is scaled in miles and handing those exact same numbers to a navigator who is reading a map scaled in kilometers.
That's a great way to put it.
The underlying data structure looks like a valid number, but the scale is completely misaligned. You just end up in the ocean, or in this case, at address 0.
That is precisely the mechanism of the crash. The Conda package manager provided a release mode fmt.dll. Inside that DLL, fmt.format constructed a std.string using the miles blueprint, the release layout, with an iterator debug level of 0.
It then returned that object by value across the DLL boundary back to the main executable.
But the main executable was compiled in debug mode with an iterator debug level of 2.
Yep.
So it received the memory payload from the DLL and interpreted it using the kilometers blueprint. It read the wrong byte offset to determine the size of the string, getting a total jump value of 15. It read an empty, uninitialized block of memory as the data pointer, resulting in a null PTR.
It is a textbook one definition rule violation, or ODR violation.
Right.
The compiler basically assumes there is only one definition of a std.string across the entire program. But because of the mixed build types, there were 2 physically distinct definitions trying to interact.
And this creates what the developers' notes called the triple whammy. This catastrophic failure requires a highly specific alignment of 3 factors to even trigger.
Right. First, it requires Windows and the MSVC compiler. If you run this exact same setup on Linux using GCC or macOS using Clang, the bug completely vanishes. Yeah, those compilers do not fundamentally alter the physical layout of standard template library objects between debug and release builds. The ABI remains stable.
Oh, that's wild. Okay, second, it requires Conda. Conda package maintainers frequently choose to only compile and ship release versions of C++ libraries like FMT and speedaylog.
Right, to minimize repository size and maintenance overhead, they just don't ship a debug variant of the DLL.
And their third, it requires the developer to actively trigger a local debug build. Because as we established earlier, the automated CI system was falling back to a source-built release configuration, bypassing Conda entirely.
Right, so you remove any single one of those 3 variables and the system functions perfectly.
Wow. So understanding the precise mechanism of the ABI mismatch, we move to the solution. How do you prevent a build system from silently injecting a toxic release DLL into a debug executable?
Well, the developer implemented a remarkably concise fix inside the cmakelist.txt configuration file. They just wrapped the dependency import in a simple guard, if not MSVC.
So, by wrapping the dependency in an if not MSVC guard, you're effectively forcing CMake to bypass the precompiled Conda packages entirely whenever it is building on a Windows environment.
Right, you're purposefully breaking the Conda dependency link.
And when CMake bypasses Conda, it drops down into the fallback CPM logic, which uses fetch content to download the raw C++ source code for FMT and build it locally.
Which solves the entire problem, because a local source build automatically inherits the exact same compiler flags as the main project.
Oh, of course.
If the main project compiles in debug mode, setting iterator or Dougal level to 2, the FMT library compiles from source with that exact same macro. The definitions of std.string match perfectly. The ABI is synchronized.
It neutralizes the vulnerability right at the build architecture level. But discovering this fix led the developer to a much larger structural realization about the ecosystem they were actually working in.
Right, because this specific cmakelist.txt file wasn't isolated. It was essentially a template that had been heavily utilized across their entire organizational directory.
Which means this exact configuration flaw, this silent ABI landmine, was lurking in 19 different sibling projects.
It really exposes the scale of the vulnerability.
Yeah, the presentation notes explicitly list the blast radius. 11 distinct code bases utilize both FMT and cblog and were susceptible.
Right, including projects like SICK-APT-TTT, NATCP, and digraph-XCPP.
Yeah, and 7 projects relied on FMT alone, such as xnetwork-cp, and 1 project, allow-go-cpp, utilized just ctlog.
If we connect this to the bigger picture, it really demonstrates the double-edged nature of modern infrastructure as code.
How so?
Well, using configuration templates allows organizations to move rapidly and standardize their environments. But when you duplicate configuration logic, you also distribute its invisible flaws across your entire fleet of applications.
Which requires a systemic remediation strategy.
Yeah.
The developer's notes call this sweeping the fleet. You don't just patch the single repository that threw the zigzag V. You use global search utilities like grep to audit the entire ecosystem, hunting down every single unguarded find package call that could potentially pull a precompiled Conda binary into an MSVC build.
And the verification of that global sweep is absolute. After applying the if not MSVC guard to all 19 repositories, the execution results just flip.
From crashing to passing.
Yet, when running the test suites in MSVC debug mode, the environment goes from 9 passes and a hard termination to 154 out of 154 tests passing.
All 766 assertions execute perfectly.
Furthermore, they validate the build architecture itself. Running dumbin /dependence on the newly compiled executables confirms that they are no longer importing fmt.dll or spdlog.dll.
They are successfully statically linking the source-built versions. The ABI mismatch is just entirely eradicated from the ecosystem.
It's a masterclass in isolating a low-level memory fault and scaling the solution to an organizational level. But the presentation notes go one step further, offering a fascinating postmortem on accountability. They have a section dedicated to analyzing who is to blame for this architectural trap.
It is incredibly insightful because it requires assigning architectural responsibility to the different layers of the development stack. Let's walk through their verdict. They point the finger pretty heavily at Conda.
Yes. The developer assigns primary blame to Conda for establishing a dangerous default.
Really?
Yeah, by shipping release only C++ DLLs and presenting them as universally compatible packages on Windows, Conda is essentially distributing an environmental trap.
There is no structural safeguard or warning signal indicating that these binaries will fundamentally corrupt memory if linked to a debug executable.
Exactly. But Conda doesn't link the file CMake does, which is why CMake shares a portion of the blame.
Right, CMake acts as the orchestrator. It silently located a release-only target provided by Conda and seamlessly imported it into an MSVC debug build pipeline without raising a single diagnostic warning or validation error.
CMake should ideally enforce strict validation checks between the build configurations of the target and the host project. And then, well, there's the compiler itself, MSVC.
I was wondering about that. How does MSVC escape throwing a link time error? Like, if the one definition rule is being violated, shouldn't the linker catch it?
In many cases, the MSVC linker does utilize pragma detect mismatch to catch conflicting configurations. But because Conda precompiled the DLLs and likely stripped or failed to enforce those pragmas across the dynamic library boundary, The linker was just blind to the ABI shift.
Wow.
MSVC is the underlying enabler here. It fundamentally alters the memory layout of core objects based on a hidden macro, yet it fails to provide robust link time diagnostics to warn the developer when two physically conflicting objects are being integrated across a DLL boundary.
And for clarity, the presentation notes explicitly exonerate the C++ standard itself, as well as the CPM source builder. They functioned exactly as designed. Based on this entire diagnostic journey, the developer establishes 3 hard operational rules moving forward.
Rule number 1. Never mix MSVC debug code with release-only pre-built DLLs if those libraries return standard template library objects by value.
Because it will inevitably result in memory corruption.
Exactly. Rule number 2. When working on Windows with MSVC, prioritize building your dependencies from source via tools like CPM or fetch content.
Because it's the only way to guarantee that your compiler flags and macros match perfectly across the entire dependency graph.
You got it. And rule number 3, which is a purely tactical one. When address sanitizer is actively aborting your process and your standard console buffers are failing to flush, immediately route your diagnostic logs to a file stream using a first stream.
So what does this all mean? We started with an impossible anomaly, a perfectly functional system that violently imploded the exact moment we tried to observe it with debugging tools.
We bypassed a continuous integration system that was blind to the failure because of environment drift.
We navigated strict compiler flags to deploy address sanitizer, catching a null pointer read deep inside a corrupted std.string.
And we uncovered a fundamental ABI mismatch driven by MSVC, altering the physical layout of memory based on hidden macros.
We observed how a tiny configuration line can silently compromise 19 different code bases, and how forcing a local source build synchronizes the dependency graph and cures the entire ecosystem.
It is a stunning reminder for anyone listening. Regardless of your field, you must rigorously question the hidden configurations within the systems you manage.
Right. Just because 2 components, whether they are software libraries, supply chains, or organizational teams, are technically connected and communicating, it does not mean they are utilizing the same underlying language or assumptions.
This raises an important question, and it's a structural concern that extends well beyond this specific C++ bug. We're operating in an industry that increasingly relies on massive abstracted package managers to assemble applications. Simultaneously, we are leaning heavily on AI code generation tools to write vast swaths of boilerplate logic.
Both of those movements optimize for speed over architectural transparency.
Exactly. They intentionally push developers further away from understanding raw memory layouts, compiler macros, and linking architectures. It forces us to ask, in an era where we rely heavily on AI to write code and massive package managers to assemble our apps like digital Lego bricks, how many other silent ABI-style mismatches, where 2 perfectly functional systems speak slightly different invisible languages, are currently ticking away in the critical infrastructure we use every day?
It is an incredibly sobering thought to end on. It brings us right back to the core premise. We have to ensure that our diagnostic tools and automated pipelines aren't secretly masking the vulnerabilities they are supposed to detect. Thank you for joining us on this deep dive. Stay curious, thoroughly examine the hidden layers of your own infrastructure, and we will catch you next time.